And you can start wherever you want.
Okay, very good. Well, thank you to Eduardo for the introduction and the invitation to talk. As advertised, I'm going to talk about making wormholes stable again, in particular axion wormholes. And this is work done in collaboration with both Gary Shiu and Nidhi Sudhir, which came out a couple months ago. So I'll try and describe what we did. It's a very brief overview of where we'll go. I'll remind you of the duality between axions and three forms in 4 dimensions, emphasizing some of the key points that will show up later in the talk. Then we'll turn to the Euclidean wormhole solutions, which are well known, and I'll describe how we can analyze the stability in the 3-form picture rather than the axion picture. And then I'll conclude with just a brief summary and some thoughts where this will go in the future. Okay, so let's go to the duality. This audience probably doesn't need too much motivation. We all know that axions are ubiquitous in string theory, and the axion wormholes themselves have some interesting connections, or I guess wormholes more generally have interesting connections with arguments having to do with global symmetries, baby universes, and so on. Axion wormholes play a special role in the axion weak gravity conjecture. They play the role analogous to black holes in terms of setting this order 1 parameter in the inequality. And so we're motivated to try and understand these classical solutions a bit more thoroughly. And one of the steps in doing that is to understand whether it's perturbatively stable. And that's the question I will try and answer. So this duality, the way I like to think about it is that you start at this top box where you have a 3-form H, and the Lagrange multiplier theta imposes the constraint that the 3-form is closed. And so if you integrate out this Lagrange multiplier, you get this constrained system on the left-hand side. And this is analogous to Maxwell's equations, which we all learn about in undergraduate classes. If you introduce a gauge potential, in this case, a 2-form gauge potential, then you can just talk about gauge transformations. You can look at this unconstrained system, but with lots of extra ambiguity. On the other hand, if you start again at the top and complete the square, you can integrate out the 3-form first. And what you find is a theory for the scalar, which began its life as a Lagrange multiplier and suddenly becomes dynamical after getting rid of H. The thing that I want to emphasize is that in going through this duality, of course, all these arrows go both ways. In completing the square and integrating out H, there's a boundary term which should be included. And we're going to be looking at this box on the left-hand side, but in analogy with the axion, there's always this extra boundary term that shows up and needs to be treated accordingly. Okay, in terms of what observables can be computed, we have path integrals, which you can evaluate either in this axion language or the 3-form language. And what's done is that you can impose boundary conditions for your metric and for your 3-form, and these are in 1-to-1 correspondence with boundary terms in the action. So this GHY term, Gibbings, Hawking, and York boundary term is there exactly because you want to impose Dirichlet boundary conditions on your metric. The 3-form under this constraint, just with this kinetic term, will have a variational problem which you should impose Dirichlet boundary conditions for. This boundary term that I emphasized on the last slide, when you translate to the axion picture, now corresponds to imposing different boundary conditions on the axion. So you have Neumann boundary conditions and Dirichlet on the metric, whereas before they were both Dirichlet. So this is one of the differences that arises in the duality, and what I'll argue for is that when analyzing the stability, it's a lot more natural to do this in the three-form picture where everything is treated democratically. Okay, so often what we want to do if we can't do the path integral exactly, which is most of the time, is to make some kind of approximation. One that's quite handy is the saddle point approximation, where you just look for classical solutions of the equations of motion, and then you can imagine perturbing around it. Here I've now switched to Euclidean signature, and this overbar is indicating the classical solution, and then around it the perturbations are these delta phi's. And the question of stability amounts to looking at eigenvalues of this fluctuation operator, capital O. Now, if this functional determinant is positive, that indicates that it's a true minimum of the action as opposed to a saddle point. Whereas if the determinant has if there's a negative eigenvalue, that's indicating a stability. And what this path integral would then compute is the non-perturbative tunneling rate. There's one thing which will show up again a little later on, which is when you have dynamical gravity, Einstein-Hilbert term is not bounded below in general. If you make some conformal transformation of the metric, you can add some terms that decrease the value of the action. And so it seems a priori that you would never be able to find minima of the action. You would only ever find saddle points. So more on that later. And then just as an aside, you can ask the question of, if I find a collection of saddle points, a whole bunch of different classical solutions which all satisfy the boundary conditions, you could ask which saddle points should I sum over? Should I include complex metrics? Should I stick to Euclidean solutions? Should I only sum over minima, or should I include proper saddle points as well? So we have a section in our paper discussing this for the axion-gravity system and the three-form gravity system, but let me not discuss that here. In the axion-gravity system, there's a well-known saddle point, which is our focus. It's the Giddings-Strominger wormhole, which I've written here in two coordinate systems. So the first line makes it clear that the asymptotic regions are flat space. You have R going to plus infinity, and then also the reflection of this being just flat space and spherical coordinates. And in these other coordinates, it makes it clear that it's conformal to a cylinder. So it does have this wormhole geometry. All of these cross sections are S3s. And then this radial coordinate you can think of as being just the size of the cross section, whereas the X is giving the distance along the wormhole. So in the solution, the three form is constant. So on each of these cross sections, you have some isotropic flux. And if you want, you can think of this as being some vector field from one side to the other. So there's an orientation to the solution. If you glue the two ends together, it's acting like a dipole. There's some flux quantization, but I'll stick with this n tilde, which is quite convenient where we're going. Okay, so that finishes the the motivation, the background, and now we'll get into the weeds of talking about the stability. Maybe I should pause if there are questions at this point. Okay, very good. So this wormhole solution, it's particularly symmetric. It has this O4 symmetry from these S3 cross sections. And then, so the question we want to answer is whether it's unstable to both homogeneous perturbations, but also inhomogeneous perturbations, where we take that cross section and squash it in some way. There are some difficulties in doing this with the axion picture. So I'll present the results for the three-form side of things. And then just to kind of tie this to everything else that people are thinking about, this is an important question to answer when it comes to ADS, CFT, and factorization. These connected geometries are somewhat puzzling from the standpoint of the boundary CFT where partition functions will factorize. A little bit of history. This is just to show that this is a very difficult problem, but also to demonstrate that I think the consensus has finally been reached. So there are a few things that a description of the stability should have. First of all, the conclusion whether it's stable, everyone should agree on. You should do things in such a way that you're only talking about gauge invariant degrees of freedom. When I come to discuss the different angular momentum sectors, there are two that are somewhat special, the j=0 and the j=1 sectors. And so what we found is that those are pure gauge as well. And then, so a lot of the recent works found this as well. And then maybe most crucially is the boundary conditions. You want to impose either Dirichlet on the 3-form or Neumann boundary conditions on the axion. And so you can do this in both sides. The axion picture is a bit more subtle, so I'll try and point out where that comes about, and I'll present the results for the 3-form. Okay, so we'll do this in a few steps. We have to parameterize the scalar perturbations. I already told you there are boundary conditions. We have to get rid of unphysical modes. So there are diffeomorphisms, which make some of the scalar perturbations redundant. There are some fields which are non-dynamical and should be integrated out exactly. And we'll be left with an action which is describing just the physical modes. And this is the thing that we should look for, whether it's a minimum or a saddle point. And this we can do by analyzing the spectrum of that fluctuation operator. So we have 6 scalar perturbations. There are 4 associated with the metric. These are fairly standard. This is the onsets that one usually makes if you're looking, for example, at cosmological perturbations. And for the 3-form, there are 2 scalar perturbations that we can write down. This S and W. So one's a homogeneous perturbation, the other is inhomogeneous. And these are tacked on to the background solution, which is order 1. Now you might ask, okay, why are there 6? If I do this in the axion picture, I would only have the 4 for the metric and then the scalar itself, that would be 5. But of course, we've yet to impose the constraints on the system. The fact that DH is constrained to be 0 will relate W and S to one another. And for all 6 of these perturbations, they should go to 0 at the boundaries. So as I said, some of these are not physically measurable or distinguishable. There are diffeomorphisms which make some of the scalar perturbations redundant. So here there are transformations. H is some Hubble scale that is time dependent or radius dependent. And what we'll find is that the scalar perturbation that survives is this gauge invariant combination here. So I've called it capital S. Is some linear combination of both the 3-form scalar perturbation and the metric perturbation E. So by design, it's scalar, it's diffeomorphism invariant, and everything else will either be gauge redundant or non-dynamical and integrated out. The action that these perturbations live in is shown here. It's a bit of a mess, but there are a few things that I want to highlight. One is this Lagrange multiplier that we saw before. Here is exactly that constraint that DH should be 0. That will let us express W in terms of the perturbation S. The other thing is that not all of these are dynamical. We have kinetic terms only for psi, E, and S, I guess, here. And the other thing is that this conformal factor problem that I mentioned is alive and well. The kinetic terms on this first line are all negative definite. So if you think of this as T minus U, this first line is something like minus Q dot squared. So seemingly problematic. But as I'll show, these are not physical degrees of freedom. And by imposing the constraints, these seemingly problematic terms will get either thrown away or get reabsorbed into some physical degrees of freedom where the kinetic term is positive definite. So because the background is O4 symmetric, we can expand in angular momentum states and just look at each of the sectors independently. As I mentioned, the j equals 0 and the j equals 1 are somewhat different. Those are the ones that I'll show some details for, and then the rest can be treated identically. So let's look at the homogeneous modes. These are where the angular momentum is 0. A lot of those terms will die away. You have anywhere there's a delta, it just goes to 0, and you're left with just these terms, which only involve the metric perturbations. But I should emphasize that the axion or the 3 form is still playing a role. There are terms in here which come from the h squared term, but doing the contractions with the perturbed metric instead. So schematically like this, the terms of the potential do depend on that 3 form being present. Okay, so now we'd like to understand this. We have one non-dynamical field, this phi 0. And so we can perform its path integral exactly. It's some Gaussian that you integrate over. And what you're left with is maybe not too illuminating, but it turns out that this is actually a total derivative. And so the interpretation is that there are no physical degrees of freedom in this homogeneous sector. This is somewhat mysterious, and I think there's a better way to understand this. If you write this in a first order form, so you introduce a momentum for the dynamical field psi, you write it as, this is like PQ dot minus H, and you find that the non-dynamical field phi appears linearly, which means that it imposes a delta function constraint between the momentum and the field itself. So this would appear as a delta function after integrating over phi. And importantly, the delta function constraint is a gauge invariant. So it does physically make sense to impose this on the field and its momentum. Okay, so that's the general story. When you go to the higher angular momentum states, sectors, it becomes a bit more involved where those terms stick around. Here again is the j equals 1 sector, which also turns out to be a total derivative, and you have no dynamical degrees of freedom that show up. The process is exactly the same, and you can find that those delta function constraints are, again, gauge invariant. So that's an important detail. Somewhat unsatisfying so far. We have yet to find any physical scalar perturbations, but if we go to j bigger than or equal to 2, then we find that there's actually one scalar perturbation that survives this process. You start with the 6 scalar perturbations, you impose one constraint from the Lagrange multiplier. You have 3 dynamical fields and 2 that are non-dynamical. And after imposing the 2 delta function constraints, like I just showed, you find that the mode that survives is exactly this gauge invariant combination. And the action that describes its that describes this mode is a bit complicated. There's some prefactor which is known. We know the eigenvalues lambda. We know the background geometry A, and we've been careful to keep around all the boundary terms for this physical mode. So I've written here this S dot S term. There's some kind of potential term here as well. And now the question is this quadratic action positive definite or not? Now, the way we answered this, you could imagine just taking this and massaging it into a form where it's a sum of squares, but we wanted to complete the story in such a way that we find the eigenvalues as well. And to do that, you can normalize your fields and you boil it down to a standard quantum mechanics Sturm-Liouville problem, where we have some like a 1D Laplacian and a potential that this field is restricted to. I guess you have a Sturm-Liouville problem for each value of j. And the boundary conditions, there's a bit of work to trace through. This thing in brackets here is the prefactor that shows up in the action. So it's some known function of R. And the fact that S and E have to go to 0 tell us that this gauge invariant combination has to go to 0. And then with the prefactor there in our normalization, we actually learned that the Q has to go to 0 faster than e to the minus r. And in the Sturm-Liouville problem, that corresponds to exactly looking for bound states. And luckily, we can do this exactly when we have large angular momentum. So what I've shown here on the left are some of the potentials. The lowest one down here is when you take j to infinity. And in that case, you can find the bound states exactly. They're shown on the right in the dotted lines. And then numerically, you can find also the bound states for any finite j. If you go all the way down to j equals 2, which is the lowest value, you find these eigenmodes, which are nearly identical to the infinite j case. And so in between, there's some interpolation. Now, we've been careful about these boundary terms, and indeed there are boundary terms that survive in this action. You can find these bound states and find the eigenmodes by just looking at the bulk terms here on the left-hand side. But the G, as I called them, are total derivatives. They don't influence finding the eigenmodes, eigenvalues, but they do influence the value of the action, which is what we're after. And so now, having found the bound states and their functional form, you can go and ask, what is the value of this total derivative? We expect it to be 0 just because the perturbations are dying away at infinity. But interestingly, what we find is that for these odd modes, this total derivative does indeed integrate to 0. Whereas for the even modes, this total derivative is not integrable. So there's some divergence near the wormhole throat, or if you try and integrate over the total derivative, you get something that's diverging. Importantly, it diverges in the positive sense. So here, the total derivative term is diverging to plus infinity. And so you can imagine turning on some of these perturbations. If you turn on the even mode, then the action gets very large, more positive than it was for the symmetric background. And if you turn on the odd perturbation, there's a finite change to the action. And indeed, we can find these eigenvalues numerically, and then we know the exact solution as j gets large. And all of these eigenvalues are positive. So the details, of course, don't matter too much here. Just the fact that they're positive is enough. So whenever you turn on these odd perturbations, the action increases. And so we conclude that the GS wormhole is stable. It's a minimum of the action. Okay, so maybe for the sake of time, let me skip this, but if people are interested, I can expand on this difference a bit more. So that brings me to the end. So let me just summarize. I reminded you of this duality that we have in 4 dimensions. And for the axion or 3-form gravity system, we have a nice symmetric saddle point that we like to explore. And by looking at the stability in the 3-form picture, we get a fairly straightforward stability analysis where the scalar perturbations, we find this gauge invariant combination, which is mixing the 3-form and the metric together, impose Dirichlet boundary conditions on this combination, and we find a spectrum which is everywhere positive. As I mentioned near the beginning, these wormholes, these connected geometries are somewhat puzzling for ADS-CFT, so it's kind of it's a very interesting question to ask if you can embed these in some top-down description of ADS. I've said ADS, of course, the wormholes we looked at, and the stability was all done in flat space. And so there's this question of whether if you do this now in ADS boundary conditions or with the dilaton, which often comes along with for the ride, whether the conclusion about stability remains the same. If you're puzzled by this factorization problem, you might wonder if there are other degrees of freedom or other saddle points which somehow exactly cancel this wormhole contribution, or even if this is a problem at all, you might entertain the possibility that factorization shouldn't be part of ADS safety. Maybe the wormhole geometry should be there and not canceled at all. So there are a few references if you're interested, that at least that I'm aware of, where you can explore this question. So with that, let me end and thank you all for your attention.
Thank you. Thanks for this very nice talk. Let's all give a big round of applause to Gregory. So we have some time for questions. Maybe while we wait for some question, I will ask you something. So you showed a table with previous results regarding stability. So I understand that maybe in these references, their computations were different or they were in a different gauge, but in principle, the physical results should be the same. So can you comment a bit on, are your results the same as they did, or what is it that they did differently in these references, and is everything consistent? Or?
Yeah, very good. So to my knowledge, the first stability analysis was done back in the 90s. And the most glaring issue with the first one is that they were not working with the gauge invariant perturbations. And so it's not necessarily meaningful that you show that something that's off shell is a minimum or not a minimum. I guess they find it not to be stable. So there's some direction of off shell perturbations where the action decreases, but this is not surprising at all. More recently, the issue with doing it in the axion picture is that you have, if you're looking for some gauge invariant variable, you might imagine, at least schematically, you'd have some metric perturbation and then some axion perturbation, because I've been calling it theta. Neither of them is independently gauge invariant. So you need to take some linear combination where the sum is gauge invariant. And then it becomes a lot more subtle about what boundary conditions are being imposed. These guys are Dirichlet. These guys are Neumann. And I think at face value, you would look at this and say that there's some kind of mixed boundary condition that should be imposed. And my understanding is that the earlier works didn't account for this. So in changing the boundary conditions, you're changing the problem entirely.
But okay, I see. Okay, I see. So that's why you did everything with the free form, no? So that the boundary conditions. Okay.
Yeah. So with the free form, as I described, this S minus delta E, both of these are Dirichlet, and so it's clear that you should impose Dirichlet on the combination as well. Mm-hmm. Now I should say that I've been schematic here with the coefficients. You can do this more carefully and make the computation work with the axion as well. So that's what these folks have done as well.
I see. Okay. Thank you for the answer.
Mm-hmm.
Any other questions? No, everything was very clear. Okay, well, if there are no more questions, I will stop